All right. Hi, everybody. We should be on page 1 of your notes. You'll notice just 2 designs they have here at the top, but we're going to start right here. I want you to draw a circle with center O. So you can either use your compass to do this. I'm going to use my compass just for because of my lack of drawing skills. You're going to need a compass for this lesson. So pause the video and grab a compass if you don't, compass and straight edge if you don't have one already. Okay. But here's our circle, and the center is O. And you should know from previous years in math, I know you haven't done circles in a couple years, but the radius is this distance from the center of the circle to some point on the circle. So it says any point that we pick, P, has to be either inside the circle, outside the circle, or on the circle. So for any point P, how can we use that distance to determine if it's in, outside, or on the circle? So first of all, let's start with if it's on the circle. On the circle, then obviously P on the circle, then obviously that distance OP, that length, has to be equal to the radius, or equal to R. So now, what if P is outside the circle? If point P is somewhere outside the circle here, then this distance OP is going to be greater than the radius, right? And lastly, the other situation that can happen is if P is inside the circle, then that distance is going to be less than the radius. Okay, so at the top of page 2, there's a new vocabulary term here that's going to be important in our key concepts. That word concentric. You can almost see the word center in there. The 5 circles in the above design are concentric. Take a look at these circles. See how they concentric, you can almost guess what that word means. That means they share the same center. They have the same center, but different radii, obviously. If they had the same center and the same radius, then they'd be the same circle, so different radii. Why are they similar to each other? Well, that's just because we can dilate one onto another let's say map one onto the other. Map one onto the other by using a dilation. So if we just made one of those larger, we scaled it, they would map onto each other. Okay, conjectures is just like a guess. It says the longest chords, that's another one we're going to have to talk about. What is a chord? You probably haven't heard of that. A chord is just any segment in a circle. So here's an example of a chord where the 2 endpoints are on a circle. So that's a chord. This is the longest chord are the diameters, true or false. That's this diameter word I do expect that you've heard before, but the diameter, it passes through the center, right? The diameter has to go directly through the center of the circle. So do we all agree that, yeah, if it's passing through the center, that is going to be the longest? It should be true. And in the decorative design above, the sides of the square are chords of which of the 5 circles. So it's talking about these sides of the square. Here they are. Which one are they chords of? They're chords of the largest circle, right? They're segments that are inside that largest circle. So they are chords of the largest circle. What can you say about the sides of the square in relation to the second largest circle? Well, let's see. If we look at the second largest circle, here it is. I'm just tracing it. The sides of the square are what to that? What's the word that we use in math to when it just touches it perfectly but doesn't intersect? Hopefully you know, but that's called tangent. So the sides of the square are tangent to the second circle. Okay, so basically right now we just have tons of vocab that we just did. I want you to pause the video and see if you can fill these on your own. But I'm going to fill them in. So blank circles are circles with a common center. That's called concentric. A blank is a line segment whose endpoints lie in a circle. That's a chord. And let's draw ourselves a picture over here of a chord. So segments, there we are. The longest chord in a circle is the diameter, which has to go through the center of the circle. So we can draw ourselves a picture of a diameter too. Very good idea. There's a diameter. It's double, two radii, right? Make up a diameter. A line blank to a circle only touches a circle in exactly one point. So let's draw a circle. And what does that mean if a line just touches a circle in one point? Just goes by and touches it perfectly. That word is called a tangent. And we're going to kind of focus in and we're going to do a theorem on this, on a tangent line right now. So make sure you have your compass and straight edge so that you can discover the theorem on the next page. All right. So at the bottom of page 3 here, we're going to draw a circle with center O and radius R. So I'm going to draw myself a circle with my compass. And the center is O and the radius is R. Next, place a point anywhere on the circle and call it A. Okay? I'm going to call this point A. Draw a tangent line through the point. So tangent line from the previous page has to just touch the circle in one spot. So it's just going to touch it at point A. So if I want to draw a line that's going to touch at point A, it's going to look like this. So take your straight edge. You should be using your straight edge on that point too. This is called the point of tangency. It says relative to R, what is the length of OA? OA is R. That's equal to the radius. Suppose B is any point on the tangent line other than A. So B is any point on this line other than point A. So here's point B. How long, relative to R, how long is OB? Well, since it's on the exterior of the circle, it's going to be longer than the radius, right? So we're going to say B is on the exterior. So OB is going to be greater than R. Now it says find the measure of the angle made by OA. If you have a protractor, fine. If you don't, it's not really a big deal. But if you can almost kind of see it, probably some of you already see it. That angle, though, is going to be exactly 90 degrees. So when you draw a radius in a tangent line, that's going to be forming a 90-degree angle. So that's huge. We're not going to really write a conjecture or make that too formal, but really, that's saying that if I have a circle and if I draw a tangent line, sorry for the horrible picture, then a radius is going to be, and I draw a radius in, that's always going to make a 90-degree angle. So basically, radius and a tangent line are going to be perpendicular, which is huge because that's going to give us right angles, right triangles, all sorts of stuff. Okay, so here it says if a line is tangent to a circle, then it is perpendicular. It's going to be R. The opposite's also true. If you see a radius and a line being perpendicular, then that line has to be a tangent line. So if it's making a right angle, then it's a tangent line. So let's draw ourselves a nice picture here. I'm going to actually use my tools this time since I'm horrible at drawing. So here's a circle, and then I'm going to draw a tangent line. And I'm just going to put arrows on it to make it a line. And then I know that that point that touches right here, if I draw in a radius to that point, then this is going to make a 90-degree angle. That's our theorem. So this is our big theorem, is that we know that tangent lines and radii are perpendicular. Okay, so now we get to do construction. Pause the video and grab a compass if you don't already have one. But okay, so I'm excited about the construction. Construct a line that's tangent to circle C at point D. So before we were just doing a sketch. Can we just draw in a line that we think is perpendicular here? The answer is no. That would not be a construction. We have to actually construct it perpendicular. So what I'm going to do is you should take your straight edge first, and you're going to connect points C and D. You're going to make a radius. So now what I know I want a right angle at D. I want to make a perpendicular. So what I'm going to do is that I'm going to use my compass, and I'm going to measure this CD with my compass. And then I'm going to mark off that same exact length out here. Why? Because now I've just created, if I extend this out, I'm going to take my straight edge and extend this line out. I've now just created a segment here, a segment with these endpoints. I'm going to highlight them in green, where D is right in the middle. So now I can make a right angle there by using our good old perpendicular bisector. Open up more than halfway. Arc above, arc below. Go to your other point of intersection, arc above, arc below. And now you should definitely be taking your straight edge and making, look at that perpendicular line. So pretty. Okay. Yay. Perpendicular. Rewind the video and look at it again. Try it again on your own. Draw yourself a circle off to the side and try it again if you need another one of those. That's going to be shown back up on a test. Okay. What is the length of BO? So let's see, the radius is 4. And AB is 3. We know that this is a right angle. Oh God, I just put that 4 in the wrong spot. Just kidding. Sorry. Oh boy. The 4 is the radius. This is the 4. Radius goes from the center to the point of the circle. Okay. What is the length of BO? I know it's a right angle from our theorem, right? Tangent line, radius, perpendicular. So BO, since we have a right triangle, we can use pi seg. It's going to be 3 squared plus 4 squared equals x squared. Those of you who know your triples don't have to do the math. You guys already know. But it should be 25 is x squared, so x is 5. So BO should be 5. Then down here it says if AB is 5 and AO is 12. All right, I'm just going to redraw the picture. So we have A, B. See, if if AO is 12 and BO is 13 and this is 5, how come we know that this has to be a tangent line? Well, because 5 squared plus 12 squared equals 13 squared. We could check that. We'll show it. 25 plus 144 equals 169, which means that these that this has to be a right triangle, so that has to be a right angle. So we'll just say since a squared plus b squared equals c squared, the triangle must be right. The triangle must be a right triangle. So it is a tangent line. Okay. One more kind of theorem for today. So it says, if these are tangent lines, how could you use congruent triangles to prove that this is congruent to this? So we want PA to be congruent to PB. We're not going to really write a proof here. Oops, I just wrote the same thing twice. We want PA to be congruent to PB. So what we're going to do is we're going to use congruent triangles to prove these triangles congruent. So pause the video and see if you can find pieces by yourself. You should have gotten that OP is congruent to OP by the reflexive property. Again, I'm not really writing a proof. I'm just like finding the pieces of it. we know that tangent lines and radii are perpendicular. So angle 1 and angle 2 are going to be congruent, right? So let's just say right angles, which are going to be congruent from our tangent lines and radius. That's our theorem we just did. Okay, so we have a right angle, we have a reflexive side. The other piece is going to be these radii. If you have the same radii in a circle, they have to be congruent. So your other piece is going to come from OA being congruent to OB because all radii are congruent. So now these triangles are congruent by, it's actually good old hypotenuse leg. Woo! It's from a long time ago. All right. And then obviously PA is going to be congruent to PB by CPCTC. So basically our theorem that we just proved on the previous page is that if I have two tangent lines, if I have some point on a circle, okay, not on a circle, outside the circle, any point outside the circle, I'll do a few of them just to show you. If I draw two tangent lines to the circle from that point, they have to be congruent. So if I pick another point and I draw two tangent lines to the circle, they have to be congruent. So segments drawn tangent to a circle from the same exterior point are congruent. And let's give ourselves a better picture of that, because my picture is not good, surprise, surprise. So here, I'm just going to give you guys a better picture. And let's draw in our tangent lines. So I'm going to pick some point, P, and I'm going to draw in tangent lines. And they have to be congruent there from the same external point. Okay, there's a bunch of practice questions. I want you guys to do them on your own. You really should be able to do them on your own. I will put the answers in the lesson and I'll talk through a couple of them. But your job is to finish the day here. You see you're doing practice problems 1 through 9, and then you're going to get the homework, okay? And you should probably have time to do the ones in the notes and your homework in class. So pause the video here and then just use it to check your answers. You shouldn't really, I'm not even going to go through all of these. I'm mostly just going to put answers in. But I want you guys, like if I was here, I would be making you guys do these on your own. Okay, so go ahead and try them on your own before you look at the answers, please. Okay, so here, line segment AB is tangent to circle O at point A. Which type of triangle is formed? That is a right triangle, since the tangent line. This one, you should have set these equal to each other. And you should get that x is 5. Okay, number 3 is a little bit tricky because number 3, you have to see that if this is a radius as 12, then this is also a radius. So now when you do Pythag, you have, this is 20 and this is 12 and you're looking for this. So now you should be going 12 squared plus x squared is 20 squared. And again, I'm not going to actually go through and do that, but you should get 16. Number 4, the answer is just 5. These are all congruent. If this is coming from the same point, then that has to be 5. And then this coming from that same point, so that has to be 5. This one, you should be using those radii are congruent again, and you should get x is 12 when you do Pythag. This one from the same point, they have to be congruent, so that's 5. And then here, that's 2, so this piece has to be 2. And then if this is 3, then that guy's 3. So then x is 5 here. 7? Your answer should be yes. It is, because 18 squared plus 24 squared equals 30 squared. This one's an isosceles triangle, so your answer should have been 32 degrees. This one, if the ratio is 3 to 2, then that means that there's 5 equal parts, right? The ratio of AB is 3 to 2, so I'm just going to call it 3x to 2x, and I know that there's 5 equal parts here total on the whole thing. And then it says that this is 35. Okay, well, this is going to be the same thing here. If this is 3x and this is 3x, this is 2x and this is 2x. So now I have to break those 35 into 5 equal parts. Or if you want to set up an equation and solve, you don't have to. Some of you are just going to do this in your head. But that means that each equal part is 7. So now find DE. Well, DE is just going to be 2 of those parts, so it's 14. Right? So I just found that each of those little parts are going to be 7. There's the 5 equal parts. Okay. Good luck on the homework. So the enclosure, our 2 big theorems for the day were that if you have a radius and a tangent line, they're going to be perpendicular. And if you have 2 tangent lines from the same point on the outside of the circle, they're congruent. Good work, guys.